All right, fantastic. Everybody should be able to see the presentation now. We should be all set to go. Good morning. Happy Tuesday morning. It's a great day for pre-calc. Every day is a great day for pre-calc, but today it especially is a good day because we are going to be starting. I don't want to say something new because it is still related to our identities. We're still going to be tying it in with the proofs and all that fun stuff. But they are different types of identities now called sum and difference identities. So that's what we're going to get started with today. You may notice that I did post a little do now for you of the unit circle exact values. I would highly recommend that if you have it on you, you dig for and find this exact value sheet that you should see on your screens right now. I know I gave one of these to everybody, a filled out exact value sheet. That will be very, very handy to have going forward, starting today and going forward for the rest of our classes. In case you do not have that, I did post it on the most recent Google Classroom post, like attached to the practice work on this stuff. I can post it again as just its own thing so it doesn't get lost in the shuffle. So I'll be happy to do that again for you. But please make sure that you have this on hand. Having this handy is incredibly, incredibly useful for you. So you do not want to go without that because we are going to be using those unit circle exact values now in approaching these sum and difference identities. We'll talk about what they mean in just a little bit. Okay, couple reminders before we go ahead and get started. Number one, make sure that if you haven't done so already, that you've muted your microphone and your webcam is disabled. I'm pretty sure we're all on the same page with that. Make sure that you submit your attendance form for the day. It's on Google Classroom. Just fill that out. And last thing I want to mention is about the progress assessment. I did post the answer key to the progress assessment this morning. I will make sure to get those grades in Aspen by the end of the day today. So what I'd recommend that you do is please make sure you take a look at your progress assessment, take a look at your answers, and say, compare the two, and hopefully that should correlate with a reasonable grade that you received. But if you do have any more specific questions or need more specific feedback, please reach out. If you're like, Mrs. Giorgio, I don't know why I got this grade, or Mrs. Giorgio, do you mind going over problem number 4 because that one was particularly challenging? I'd be happy to do that during my office hours with you. Okay, just let me know. Send me a Hangouts message. I'll see you there. So, with that being said, let's now go ahead and approach these exact unit circle values. I'm going to be relying on you to actually participate in the chat. What do we got for some exact unit circle values? We're looking at the cosine of 30 degrees. What do we got? Cosine of 30 degrees. Bam. Should be off the top of your head. Haven't done unit circle in a while. Doesn't matter. It should be drilled in. Cosine 30 degrees is what? Anybody. Somebody. Cosine 30. Oh, that's sine 30, Dave. Sine 30 is 1/2. Super close, though. Sine 30 is 1/2. You're on the right track.
Square 3/2.
Rad 3/2. You knew it was going to be one of them. You knew it was going to be one. It was a coin flip. We got Adam. We got Jake in the chat. Rad 3/2. Absolutely. Cosine of 30 degrees is rad 3/2. Okay, keep that in mind. Rats. I know. Rats. It happens. It happens. How about the sine of 135? Sine of 135 degrees. That's second quadrant. It's one of your pi/4 angles. What's going to be the sine of 135 degrees? We got a negative rad 2/2, says Jake, which is super close. I wouldn't say it's negative, though. I wouldn't say it's negative. Super close. Can we get someone to swoop in with that correct answer? Positive rad 2/2. Absolutely. Why is it not negative rad 2/2? The cosine would be negative rad 2/2 because cosine in the second quadrant is negative. But remember, when you're dealing with sine, the first and second quadrants are positive because it talks about y. So this would be positive rad 2/2. That's okay, though. This is all dusting off the cobwebs, right? How about the cosine of pi/3? Bam, cosine pi/3. Cosine pi/3? I know you know that. Cosine of pi/3. We got some people thinking. Cosine pi/3. 1/2. Dave with the redemption story right there. Absolutely. Cosine pi/3 is 1/2. Very good. And last but not least, how about the sine of 4 pi/3? Sine of 4 pi/3. You know all the over 3's share the same cosine and sine. Just think of now, so you could say, well, that's the same as the sine of pi over 3. Just think of where it would be positioned on the unit circle. That is Jake coming in with a big answer right there. That's going to be negative rad 3 over 2. Absolutely. It's rad 3 over 2 because the sine of pi over 3 is rad 3 over 2. And the reason it's negative is because that would be in your third quadrant, right? Because it's greater than 3 pi over 3. Therefore, it's greater than 180 degrees. So it'll be in the third quadrant. I know, especially since we're doing the distance learning now, that stuff is probably not as fresh as it would be if we were in class. If we were physically in class, you better believe I'd be drilling everybody every single day. Look at that classroom camaraderie in the chat section as well. Everyone's like, thank you, great job. I appreciate you, and I appreciate you guys too. So that is, but it is important that you do know, I say at least the first quadrant ones. Like if I said, especially going through a pre-calculus class, you are definitely expected to know that the cosine of 30 degrees is rad 3 over 2, going forward. The sine of 30 degrees is 1/2. The cosine of 45 degrees, rad 2 over 2, as well as the sine. The tangent values are important as well. We're not actually going to talk about the tangent sum and difference formula because it gets a little messy. We're just going to stick with sine and cosine, but still, those are important numbers that you should be aware of. If you're not, however, you do have that unit circle exact values chart, and I highly, highly, highly recommend that you make use of that for really the rest of the year. Make sure you locate it. If you need a copy, I did post a copy for you, and make sure that you have that on hand because it will be very, very handy. All right, anyway, so after that little unit circle refresher, right, we can do something like the cosine of 30, sine of 135, cosine pi over 3, sine 4 pi over 3, no problem, right? Those are all simple things that we can do because they just involve the unit circle. They may take some little bit of memory to recall it, but it's more or less just think about the unit circle or look at the unit circle and figure out where you are. What if I gave you something like this? What if I said, could you tell me what the sine of 75 degrees is? Okay. Well, as David said a little earlier, rats. Rats. 75 degrees is not one of our special unit circle values, right? It's not 60, 30, 45, 90, 0. It's none of those. It's just some random, seemingly random number, sine of 75 degrees, right? Well, we'd be a little stuck here if not for what we're going to learn today, which is the sum and difference identities. There's really no good way to approach this as of now, but we do know two angles that can definitely help us get this 75 degrees, right? Is it accurate to say that the sine of 75 degrees would be the same as the sine of 45 degrees plus 30 degrees? Ooh, 45 plus 30 is just 75. That's just another way to write 75, but maybe the wheels are turning a little bit. By writing 75 as 45 plus 30, maybe you can now think, oh, wait a minute. 45, that's a sine value that I know. 30, that's a sine value that I know. Can we somehow stick them together and come up with a way to actually express that that can help us find the sine of 75? And the answer to that is yes. And this is what leads into what's called our sum and difference identities. Our sum and difference identities are written as follows. Okay? Ready? If I have, and this is super important, please write this down. Okay? Your identities, sum and difference. And the reason they're called sum and difference is because if you have two sine values, a sine of something plus something, or the sine of something minus something, sum and difference, or cosine as well. Okay? Identities. We'll do sine first. The sine one is, it says the sine of, it uses the Greek letters alpha and beta typically in the definition, so I'll just say A and B. The sine of A plus B for any values A and B, right? The sine of A plus B for any values A and B is written as the cosine of A times the sine of A plus the cosine of B times the sine of B. Okay? Let me just double check that just to make sure, but I'm pretty sure that's what it is. It's 4 sine. I'm just double checking. I just want to make sure. I don't want to give you the wrong thing, but I'm almost positive that's what it is. It's sine, cosine. Oh, it's the other way around. It's the other way around, plus cosine sine. I guess it wouldn't particularly matter, but it's typically written as the other way around. So hold on, let me reverse that for you. It's typically written as sine of A, cosine of B. So this is written as the sine of A plus B. Let me do it nice and neat down here. The sine of A plus B is written as the sine of A times the cosine of B plus the cosine of A times the sine of B. There we go. That looks a little better. Okay, that's a little more familiar. Sorry about that. So the sine of A plus B breaks down to be, it's equivalent to the sine of A times the cosine of B plus the cosine of A times the sine of B. The same is true for minus, right? And so the way that this is typically notated is you would say it's the sine of A plus or minus B is the same as sine of A cosine B plus or minus cosine A sine B. So in any case, if this is A plus B, then this is going to be a plus. If this is A minus B, this is going to be a minus. All right, but that's exactly how it breaks down. There is a similar breakdown for cosine. Okay? The cosine of A plus or minus B breaks down to be, this is, I believe, it's cosine stays cosine, right? Yeah. We got cosine A, cosine B. The way that this is typically written is minus plus sine A, sine B. And what does that notation actually mean? That means that the cosine actually changes signs when you go from its normal definition to the breakdown. Okay? Sine stays the same. The sine in sine is the same. The cosine goes to its cosine. That's a cheap little memory trick that I usually use. It's kind of lame, but I always say, oh, the cosine matches with its cosine. It's for its other partner sine. If you have A plus B, the formula breaks down to cosine A, cosine B minus sine A, sine B. If you have A minus B, it breaks down to cosine A, cosine B plus AB, sine A, sine B. Okay? And those are what are called your sum and difference identities. So how does that actually help us going forward? Well, the way that would actually help us is we can use these identities now to break down something like that. You could say that the sine of something like 75 degrees, correct, is the same as the sine of 45 plus 30. Using our identity now, we could now say that the sine of, I'll just rewrite it here, 75 degrees is the same as the sine of 45 degrees plus 30 degrees, which according to our identity, we can write as sine of A plus B. We could say it's the sine of 45 times the cosine of 30 plus the cosine of 45 times the sine of 30. And if we were in class, like physically, I would definitely have shown you the proof of this. The proof of this is really cool. Use the Pythagorean theorem. It's really interesting to show that. So if you're interested, you can definitely look up online and find a proof of these sum and difference formulas. If you're interested in where they actually come from and why they work. You could test it with any real numbers, though. You could type this into a calculator, this line, and press enter, and then type sine 75 and press enter, and you should get the same exact number, which is really cool. Now, we can actually evaluate this though, using our unit circle values. That's why it's beneficial to break this down to this, because now you can say, oh, well, the sine of 45, that's just rad 2 over 2. The cosine of 30, wait a minute, cosine of 30 is just rad 3 over 2. We saw that up there. Plus, the cosine of 45, that's rad 2 over 2, times the sine of 30, that's 1/2. And now just combining these together, I would get that this is the square root of 6, that's the square root of 2 times the square root of 3, over 4, that's 2 times 2, plus the square root of 2, that's square root of 2 times 1, over 4. And so this can simplify and combine into the fraction of rad 6 plus rad 2 over 4. And that is an exact value that actually represents the sine of 75 degrees. If you type that into a calculator and that, you get the same answer. Pretty cool. So just because it's not one of our special unit circle values doesn't mean that we can't work with it. We can work with it by using our sum and difference identity. Okay, let me show you another one just to make sure we're on the same page. How about something like the sine of 15 degrees? Then we'll do a couple cosine examples. Okay, sine of 15 degrees. Well, the sine of 15 degrees, we could say, by itself is not very useful to us, but we could say, hey, this is the same as the sine of 60 degrees minus 45 degrees. See, it's kind of like finding those two pairs that are going to work out nice, that pair of angles, rather, that's going to work out nicely. You could say, oh, 60 minus 45, that's how we can get to 15, and 60 is a familiar angle, and 45 is a familiar angle. So that's why, in particular, I'm choosing to go with those. Now we could say, according to our sum and difference formula, we have 60 minus 45. So we're going to break it down like this. I'm going to say that that's the same as sine of A cosine of B. So sine of 60 cosine of 45. Minus, because the sign is going to stay the same when we do sine, the cosine of A, cosine 60, sine of 45. Just like that. Okay. Now, that's just breaking it down the way my formula is defined up here. Now I can go ahead and actually use that to find out what the exact values are. Sine of 60, well, the sine of 60 we just did up there. That's rad 3 over 2. Right, sine of 60. We have the cosine of 45, rad 2 over 2. Minus cosine of 60 is 1/2 times sine of 45, rad 2 over 2. Combine all these together, we're going to get rad 3 times rad 2 is rad 6 over 4 minus rad 2 over 4. And so you would get that the sine of 15 is rad 6 minus rad 2 over 4. And by the way, these numbers of rad 6, rad 2, and 4 come up quite often when you're doing sine and cosine, because that's just how these values are going to work out. When you're doing, rad 3 times rad 2, those are common values that are going to show up in your unit circle exact values. So you're going to get rad 6. 2 times 2 is 4. Those numbers just show up often. So you'll probably see in a lot of the examples that you do just some variation of rad 6, rad 2, and 4 kind of grouped together like that. Does that make sense to everybody? Let's do just a couple using cosine. All right, let's do a couple using cosine. So just to rewrite it for you up here, remember that the cosine of A plus or minus B is written as, and again, just over here, it's cosine A cosine B minus plus sine A sine B. So we got cosine A cosine B minus plus sine A sine B. And again, that notation of minus plus, it kind of matches up with this, right? You're just saying take the sine and just do the opposite one, right? Do the cosine. It's a dumb pun, but hey, you may remember those dumb little things. You never know, okay? Just like our reciprocal dance, right? Remember that. All right, so in any case, don't think I'm not going to bust that out at the class reunion. Here we go. So now if I have something like this, right? What if I gave you an example of, jeepers, now I promise that, the cosine of 165 degrees. Okay. Cosine of 165. How can I combine two angles that I know on the unit circle to get 165? Well, let me think for a minute. Let's see. I know 135, right? Does that help me? 135 plus 30. That could help a little bit, right? Cosine of 135 is one of those special ones. So you could do 135 and 30. You could do the cosine of, I mean, there's a couple different combinations too. You could do the cosine of, let's see, maybe, trying to think of numbers that will work out nice. 210 and minus 45. That would work out nicely as well. So there's a lot of different combinations of numbers that you could actually pick, but I like going with the one that we just mentioned. Let's say that this is the same as the cosine of 135 plus 30. Right, that's how we can get our 165, right? If you remember your exact values, the cosine of 135 degrees, so first of all, let's break this down. let's say using our formula up here, this is going to now break down to be cosine of 135, cosine of 30. Since this is plus in here, it's now going to be minus here. Sine of 135, sine of 30. All right, let's see if we can work with that. I would say the cosine of 135. Well, 135 is in the second quadrant. It's one of your pi over 4 angles because it's a multiple of 5 and not a multiple of 10. So cosine of 135 is going to be negative, because it's in the second quadrant, rad 2 over 2. And again, you could use your unit circle chart to figure that out as well. Cosine of 30, that we said already, is rad 3 over 2. Minus sine of 135. Well, sine of 135 is going to be positive rad 2 over 2. Times sine of 30, that's 1/2. And then just combine these together, we're going to get that this is negative rad 6 minus rad 2, all divided by 4. And that would be the cosine of 165. Does that make sense how that works out? Hopefully we're feeling good. All right, let's do one more with cosine, and then I'll show you another kind of problem where we're almost going backwards. So how about something like the cosine of 345 degrees? Okay, cosine of 345. How the heck would I do that? How the heck would I do that? What can I combine together? Well, we could say that this is the same as the cosine of 300, it's one of our unit circle values, 300 degrees, plus 45 degrees. Right? Those are our unit circle values. We can use those, no problem. Cosine of 300 plus cosine of 45 makes 345. So let's now break that down using our cosine formula. We could say that that's the same as the cosine of 300 times the cosine of 45 minus, because the sign is going to switch, the sine of 300 times the sine of 45. Let's see, cosine of 300 degrees. I believe that's one of our pi over 3 angles. So the cosine of anything pi over 3 is going to be 1/2. Since it's in the fourth quadrant, the cosine is positive. Cosine of 45 degrees, that's going to be rad 2 over 2. And correct me if I'm wrong on any of these, by the way. And then we got the sine of 300 degrees, that's going to be rad 3 over 2, negative, because it's in the fourth quadrant, times the sine of 45 degrees, that's going to be rad 2 over 2. So let's see how we stick these together. I'm going to get rad 2 over 4 minus, looks like I got minus a negative here, so we got a negative rad 6 over 4. We stick those together now to make rad 2 plus rad 6 all over 4. Okay. Does that make sense to everybody how that works out? Keep in mind that those are, by the way, not the only numbers that you could have chosen for how to get the cosine of 345 degrees. You could have done, I'm trying to think of one off the top of my head, but I'm struggling to. But I'm sure there's other combinations of angles that you absolutely could have picked to get the cosine of 345 degrees. It didn't have to just be 300 plus 45. That's one that came to my mind intuitively right away, because I know that those are unit circle values. But there's a bunch of other ones that you could have picked, and they would have definitely resulted in the same thing. I'm struggling to think of one off the top of my head, though. Oh, well. All right, any questions about that at all? No questions? Feeling good? Feeling fine? What about in these last couple of minutes? Let me show you a couple problems that you can actually do in reverse. Ready? If I have something like this, we have simplifying the cosine of 105 times the cosine of 15 plus the sine of 105 times the sine of 15. What if I asked you to simplify a problem like that? Well, hopefully your eyes would immediately be drawn to the fact that this matches up with the breakdown of this, right? The fact that I have cosine, cosine, plus sine, sine, you'd be like, well, that's the same as our sum and difference identity, just going backwards. Since this is a plus here, if we were to condense it down, it would be a minus over here. So you could say that this is really the same as the cosine, just using our sum and difference identity from the top. I could say that's the same as the cosine of A minus B. 105 minus 15, right? That's by the sum and difference identity, going from literally the opposite, going from the actual expansion down to the little part. Notice we have a plus here. That's why it changes to minus. 105 minus 15, well, that's just 90. The cosine of 90 degrees, and the cosine of 90 degrees is 0. So that whole thing simplifies to 0. Alrighty. So I think that's super important and useful, because if you have an expression like this, why go through all the trouble of evaluating that when you could recognize, ooh, that's just the expansion of our sum and difference identity. We can go backwards to say that's the cosine of 90, and the cosine of 90 we know is 0. All right. I can show you another kind of cool example like that, where we'll use the sine for this one. I have the sine of pi over 4 plus x plus the sine of pi over 4 minus x. And if I asked you to somehow try to simplify that expression. Well, this is fun, because this is actually what's going to tie into proofs that we're going to do next class. We're going to bring back those proving the identities. I know, fun stuff. But it's cool because it's really just two expansions of the sine formula that we talked about over here. Remember, the sine of a plus b is sine a cosine b plus cosine a sine b. So that's exactly what I'm going to do here. I'm going to say that's, what, sine cosine? I'm going to say that this is the sine of pi over 4 plus x is sine a cosine b plus cosine a sine b. And now that's going to be plus the breakdown of this. That's going to be, notice, sine a minus b is going to be sine a cosine b minus cosine a sine b. So that's going to be, where is it? Sine cosine, right? Sine pi over 4 cosine x minus cosine pi over 4 sine x. Right? Notice how we broke this down to this first section, kind of like that there. And we broke this second part down to that section. Now we can combine all of those like terms, and I could say, oh, we have plus cosine pi over 4 sine x minus cosine pi over 4 sine x. Those go away. And so now I have sine of pi over 4, which, by the way, the sine of pi over 4 is rad 2 over 2 cosine x, plus, same deal over here, sine of pi over 4, rad 2 over 2 cosine x. And so how do I combine these together? Well, rad 2 over 2 plus rad 2 over 2 would be 2 rad 2 over 2, because I now have 2 rad 2 over 2 cosine x, and the 2's cancel out. And so we could simplify that whole expression down to rad 2 cosine x. And so this is going to work into proofs, because next class you're actually going to see problems that say prove that this is equal to rad 2 cosine x. And so you'd have to go through these steps in order to actually prove that. Really the same type of problem we've seen today, but just, you know, with the proof language and mentality going forward. All right? Does anybody have any questions on anything we've talked about today? Just to summarize, these are the big takeaways right here, your sum and difference identities. Okay? Keep in mind the differences in the signs as well. Sine stays the same sign. Cosine switches to its cosine. Again, dumb memory trick, but I'm telling you it might work. All right, that's all I got for you today. We're right just about out of time. I did post practice problems on Classroom, so please make sure you get those done in time for next class. It'll only be to your benefit. If you have any questions or concerns, please let me know. But other than that, I hope you have a fantastic rest of your Tuesday. Next time I see you is on Friday, so try to get this done for Friday. We will have another progress assessment on Friday on the sum and difference stuff, and we'll go forward from there. All right, thank you again for everything, and I will see you next time. Bye, everyone.
Have a nice day.
Have a nice day. Happy Cinco de Mayo, and May the 5th.
Have a good day.
See ya.